The purpose of this video is to make scientific numbers easier for you to conceive of, to have a better feel for them, to have a better grasp of large and small numbers. So with that said, we're just going to work some properties of these numbers to try to get you more comfortable with them. Let's start with 5. Start with letter A here. We have 5 times 10 to the 6th. The 10 to the 6th adds 6 zeros. So we have 1, 2, 3, 4, 5, 6 zeros. And we would call this number 5 million. For part B, now when you have a decimal here, on the part A, we could have thought of the decimal as 0.0. So I could have thought of part A as 5.0 times 10 to the 6th. That means that if the 0 were right behind the 5, I would move it 6 places to the right, and that's why you get the 6 zeros. Here it's a little more cumbersome. You have 6.5 times 10 to the 5th means that you take this decimal and move it 5 places to the right. Let me show you what that looks like. So it starts here. Here's the decimal. And I want to go 5 places to the right. That's because of that number there. So I'm going to go 1, 2, 3, 4, 5. And there's the new decimal place. Now in those spots where there's nothing, I'm going to fill it with zeros. So you can always put a 0.0 at the end of it. But what we ended up in a simpler way of looking at it is just 65,000. Now when the exponents are less than 0, they're negative, you're talking about small numbers. Here, let's think of it as 9.0 times 10 to the negative 3rd. What the negative 3 then tells you to do is to move the decimal place 3 places to the left. So we got 1, 2, 3. So the new decimal place. That means I'll put a 0 here and a 0 here. So my answer is 0.0090. And they're asking you to give it a name like I gave these other two. Well, here you're working on the other side of the decimal. So the first place is the tenths spot. The second place is the hundredths spot. And the third place is the thousandths spot. So we could call this 9 thousandths. Make sure you put the TH at the end of these because the TH indicates small. Now for the last one then, we're going to move the decimal place 7 places to the left. So if I start with my 2.6, I'm going to go 1, 2, 3, 4, 5, 6, 7. I'll put my dot here. That'll be 1, 2, 3, 4, 5, 6. So I have 6 zeros. And then I'll have the 2 6. So let's see what this is in terms of place value. So we have tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 billionths, 10 millionths, 100 millionths. Let me try that again. I think I lost myself. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths. So we could describe this as 2,600 millionths. This example is asking the reverse of what we just did. So we'll start with a 15,000, and we want to make it into scientific notation. That means we have to do 1.5 times 10 to some power. The decimal has to go after the first non-zero digit. So I have 1.5 times 10 to the something. I just have to figure out how much that is. Well, if I put it here, to get there I had to go 1, 2, 3, 4 places. So that's what goes up here. Let's take a look at B. Before I do anything, I'm going to write 6.96 times 10 to some power. Hopefully you can see that the power has got to be negative since we're talking about a small number. So to get the decimal into that spot there, I've got to go 1, 2, 3, 4 places. And so here we have a negative 4. And then finally on the last one, this is an unusual one. You do want to write 7.29. It's just unusual for them to put the 6 as well. So this is an unusual way of doing the scientific notation is usually meant to shorten the notation. This is not going to be any more convenient than the original number itself. Nonetheless, let me see how many digits we moved. Since it's a big number, we know this is positive. So we go here, 1, 2, 3, 4, 5. And there we go. In this problem, we have the arithmetic of these kinds of numbers. The idea of the author is that you'll do these by hand and you won't do them using your calculators, but you can certainly use your calculators to check yourself. Anyways, let's take a look at the first one. We have 3 times 10 to the 8th, and we're multiplying that to 2 times 10 to the 6th. Now, multiplication is commutative. That means I can do this. I can do 3 times 2, and then I can put the powers of 10 in the back. Now, we're going to make use of the fact of the exponent rule. Let me write that down over off to the side. When we have the same base, and we have one exponent, and we multiply the same base but another exponent, the rule is that we add those two exponents together. So my 10s then will be 10 to the 8 plus 6, or just 6 times 10 to the 14th power. And that's what they're looking to get for you to do, is put it back into scientific notation after you do all this arithmetic. Let's go on to B. Here it's an addition problem. We have 8 times 10 to the 5th plus 5 times 10 to the 4th. I'm not exactly sure why they put parentheses around them, but probably just to illustrate them as individual numbers. Well, for something like this, you could multiply it out if you want to. This is 80,000. Let me see, this is 50,000. This is 800,000. So you got 850,000 is one way you could do it. But I'm going to do something a little trickier. I'm going to move the decimal over one place. So I'm going to multiply 8 by 10 to give me 80. But notice I took a 10 off of here to balance that out. So I multiplied by 10 to give 80 here, but I divided by 10 in the back. The reason I did that is the following. I'm going to distribute 10 to the 4th out. And now when I do 80 plus 5, that's 85. So I have 85 times 10 to the 4th. That's not quite in scientific notation. My scientific notation needs to look like this. And plus, they don't put a dot anyways. They put a multiplication sign, but that's not a big deal. So what I did is I had to move the decimal to the left one place. So that makes this number look smaller. To keep it the same value it was before, I'm going to have to move that exponent up to 5. And there's your answer in scientific notation. The last problem is a division problem. I have 8 times 10 to the 9th divided by 2 times 10 to the 6th. I can cancel the 2 into the 8, 4 and 1. Now the other two, when you had an exponent divide, or one of these to an exponent, a base, the same base to an exponent like this, then you could do the following. You could subtract the exponents. So in here I have a 4, and then I could do 10 to the 9 minus 6, or 4 times 10 to the 3rd power, which is just 4,000. So this one, they're trying to see how the numbers are comparing to each other. So for part A, here's what they want. 120 million is less than 3 billion. So they want that statement, but they also want to figure out how many times 3 billion is 120 million. In other words, they're going to look at 120 million divided by 3 billion. Now, a billion has 9 zeros. And in fact, let me take care of the million, change it to zeros here. 120 million is going to have 6 zeros. And then 3 billion has 9 zeros. Now, one of the things you can do right off the bat quickly is you can divide the numerator and denominator by not just a million, but by 10 million. So I can take out 7 zeros just by dividing by 10 million. And I have 12 over 300 left. At this point, I can use the calculator. I think it goes in there 25 times. So we could say this is 1 over 25. In particular, we could say that 120 million is 1/25 of 3 billion. Moving on to part B. So that's the idea. We're looking at how the second is in relation to the first. So here in part B, we can see that 6 times 10 to the second is larger than 3 times 10 to the negative 3. In particular, this is 600, and this here is just 0.003. Now, how much larger is it? So this is where we go 600, that's 6 times 10 to the 0, and let me change this to its standard notation, 0. Actually, you know what? Let me come back here. I do want to illustrate something. 6 times 10 to the second divided by 3 times 10 to the negative 3. Let me cancel this out to make a 2 and a 1 there. The same thing can be true here. If I divide out this, since it has the same base above, I subtract the negative 3. But that's the same as adding it. So this is going to be 2 times 10 to the positive 5th power. Now 2 times 10 to the 5th is 200,000. So we could say 6 times 10 to the second is 200,000 times the size of 3 times 10 to the negative 3. For part C, 10 to the negative 8 is larger. Two times 10 to the negative 13. Now let's compare them with 10 to the negative 8 on the top and 2 times 10 to the negative 13 on the bottom. Just like before, I can cancel the exponent with the negative power, or the negative exponent in the denominator, by adding that number to the numerator. So we're going to get 10 to the 5th divided by 2. Let me use my calculator to give me that number then. So if 10, hit your X to the Y button, and then divided by 2. Looks like 50,000. Since there are 4 zeros there, this is 5 times 10 to the 4th. So they would like us to change 390 gigabytes to scientific notation. And giga means billion, so that a giga has 9 zeros. So what they want us to change, we have 390. A gigabyte is 10 to the 9 power. That's a billion right there. Now, they want us to put this in scientific notation. That means the decimal must go into that spot, which means it has to have moved 2 places from after the 390. Well, if you do that, when you move the decimal here to the left 2 places, you're essentially dividing by 100. So you make up for those 2 places by adding 2 to that exponent. And then we get 3.9 times 10 to the 11th. In this problem, they would like to estimate these examples without using a calculator. So I'll do as much as I can. Scientific notation will help quite a bit with that. If we start with A, take a look at this. 6,300,000. After the 6, there's a total of 6 digits. So I can write 6.3 times 10 to the 6th. And then I'm multiplying that by 2 times 10 to the 3rd. Now, as I mentioned, you can move things around. I can do 6.3 times 2, and then I can have 10 to the 6th times 10 to the 3rd. So this one isn't so bad. I'm going to have 12.6 for those two numbers, and then I'm going to have 10 to the 6 plus 3. So we have 12.6 times 10 to the 9th. Now the decimal is not where I want it. I need it to go to the left 1 spot. That's dividing by 10 if you move it to the left 1 spot. That means I've got to make up for it by adding a 1 to the exponent. For part B, we have 4.9 thousand, so I've got 4.9 times 10 to the 3rd, and we're multiplying it by 2.2 times 10 to the 6th. So I can do the 4.9 times 2.2 times 10 to the 3rd times 10 to the 6th. Your textbook is trying to get you to estimate. So I have a feeling that they would want me to use they would want me to use 5 for 4.9 and just 2 for 2.2. I'm not going to do it. I'm going to multiply them out. So remember, when you multiply things like this, you can ignore the decimals until the end of the problem. Now the nice thing is we've repeated the same thing, so I'm going to get an 8, 9 again. I'll get another 1 up there. And pull there. 7, 1. 1, 0, 7, 8. Now, if you look here, I was always taught that you count up the number of decimal places in the original numbers. So there was 1 decimal place from the first one and 1 decimal place from the second one. That means we want to put it there, 10.78. So we have 10.78. Now, if I add these exponents, I'll have 10 to the 9th power. I'm almost done. I now need to move that decimal 1 place over there, so I need to divide by 10. And then multiply by 10 on the back end. Now they were talking about estimating, so when you go to look at the answer, they may write something as simple as 1.1 times 10 to the 10th. So just be on the lookout for that. Part C, we have 600,000, so I have 6 times 10 to the 5th divided by 2.1 times 10 to the 2nd. Let me go over here with it. 6 times 10 to the 5th divided by 2.1 times 10 to the 2nd. Now I use the rule of exponents here where I'll change that 5 to a 3. And then the 6 divided by 2.1, I'm going to really estimate that. I'm not going to put a lot of effort into it. So 2.1 into the 6. You might remember that you actually did this kind of problem. Like so, you would move the decimal over so you wouldn't have to deal with a decimal on the outside. So So this is just ordinary long division. We ask ourselves, how many times does 21 go into 60? Goes in twice. Let me carry that decimal. 2 times 21 is 42. Subtract, I get 18, and then I'll bring down a 0. 21 goes into 188 times, and I'll bring down another 0. 21 goes in there at least 5 times, I believe. Maybe 6. No, not quite 6. But if you do 5 up here, I'm going to get 5 times 21 is 105. And I'll leave you with the remainder of 15 over 21. So anyways, I guess I'm just going to round to one decimal place and say 2.9. And those are a little more accurate, I think, than the book actually wanted us to do. So we want to get a rough estimate on how many times you breathe or heartbeats in a day. My heartbeat is almost always around 60 beats per minute. So let's just say 60 beats per minute. And they want to know how much you get for a whole day. So this is basically 1 beat every second, I think. So let me do that. 1 beat per second. That's simple enough. And so we would need to know if I have 24 hours. Let's first change from hours to minutes. So remember, you want hours down here and minutes on the top. So now we're in minutes. Now you could leave that what it is, but then we want to go to seconds, because I did ultimately do beats per second. And we would have a minute. If we want to get rid of the minutes, we can do this. 1 minute and then 60 seconds. And then multiply this all out. This ends up being 86,400 seconds. So that would be our estimate then for the beats. 86,400 beats. It would be our estimate. You don't have to do that. Use your own estimate if you'd like. But I think the book is banking on about 1 second per beat. Or you have a problem where they give you a table of values and you have to use it in the problem. So here we are asked, how many liters of oil are required to supply the electrical needs of an average home for a year? So this is the amount given daily. So this here is daily. First of all, I need to know how much that is for a year. So I can take, let's say, the energy used. In 1 year. So what we know is we have 5 times 10 to the 7th joules per day. We can change that and put 365 day up here and 1 year down here. And then we could get, then when we do this, it'll tell us how many joules we're using in a year. And then we'll be able to answer the question. 5 times 10, well, let's do that. 5, I'll just have the calculator do it. Times 10, exponent 7. Let me hit equals while I'm here. Now let me multiply that by 365. So it looks like we had 18,250,000,000. I'm going to do it in scientific notation. So I'm going to have 1.825 Let me come back to it. How many places are after the 1? I've got 9, 10 places after the 1. So this is times 10 to the 10th. That's how much energy they need in a year. So we'll say joules per year. Now, this here, for 1 liter of oil, we get this many joules. So we could say available energy. The energy from oil is 3.4 times 10 to the 7th joule per liter. So I think the easiest to do is to take the energy used in 1 year and divide it by the energy from oil. I don't know why I put a D there. I'll put an L back. Let me show you what happens to all of the numbers as well. So we're going to take the top number, 1.825, times 10 to the 10th, J per YR. Down here, I'm going to have 3.4 times 10 to the 7th, J per L. I'll handle the division part in pieces. For example, 10 to the 7th, I can change this to a 3. I'll handle this portion with the calculator. Now these guys right here are interesting because what happens to them is I have J divided by YR times, you flip the bottom fraction so you'll get an L over J, and this will give you liters per year, which is exactly what we're looking to do. So as soon as I get this, we're set. Let me have the calculator do these pieces. 1.825 divided by 3.4. I don't know how many decimal places I want to go. Let me do 3 places. So let's do 0.537, 0.537 times 10 to the 3rd. That's liters per year. This number is small enough to where I think you just say this is 537 liters per year. Here's the last example I want to do. There are approximately 3.8 million deaths per year in country A. They want to change this to deaths per minute. So we have 3.8 million, so I'm going to say times 10 to the 6th deaths per year. I would like to change that to deaths per minute. So let's go from years to days. So a year, if I write the year up here, 1 year, I'll have 365 day down here. So I got the years out of there. So I'm n per day now. Let me change days to hours. And the days are gone, and now we're in hours. My next step is to go to minutes, which is what they were asking us for. And so I'll put 1 hour at the top to cancel, and the bottom I'll put 60 minutes. Get rid of these hours. And what all do we have then? We have 3.8 times 10 to the 6th deaths over, we have 365 times 24 times 60 minutes. Let me get my calculator to do this. I may still have this the number up from before. No, I do not. So let's do 3.8 times 10 to the 6th. So 3,800,000. Now I'm going to divide by first 365. Hit enter each time. Then divide by 24. Hit enter again, and then divide by 60. And I'll round to a couple decimal places here. It looks like 7.23 deaths per minute.